Hello and Assalamualaikum. So in this video lesson, we'll be discussing on the tutorial. The tutorial for chapter chapter 2, subtopic 2.4. So this is one of the questions from the tutorial section in the notes. So you can pause the video and try to read the question. So we can start with step 1. For step 1, we have to draw the schematic diagram. So we have the piston cylinder device, with the stopper at the initial position. So this is state 1. And in state 1, we do know the temperature T1, which is 8 degrees Celsius, and also given in the question is the mass of the substance. So the substance for this question is the refrigerant R134A. So from state 1, the substance undergoes a constant pressure process, isobaric process. So there will be a state 2. And the piston will rise until it reaches the stopper, where the volume from the question, we learn that the volume of the substance has doubled. So meaning that the volume for the substance at state 2 here, right, the volume for state 2 here is twice the volume at state 1. Or we can write it in terms of specific volume also, since we know that volume equals to mass multiplied with specific volume. So we can write also in terms of specific volume. So since closed system, the mass is constant, so we can cancel the mass, and we can see here that the specific volume at state 2 is twice the specific volume at state 1. So the first process, we can write it down, isobaric, and expansion. Since the substance is expanding, so we can write it as a expansion process. And then there is a second process. So from state 2 to state 3 right now, there is a second process, constant volume process according to the question. So the volume, so the piston does not move anywhere. So it's a constant volume process, still is at the stopper here. And then, so this is state 3. And at state 3, we do know the pressure, 1.2 megapascal, or we can write it in terms of kilopascal. We do need to know these 2 units for pressure, and we also know the temperature. So T3 here is given in the question as 60 degrees Celsius. So state 2 and state 3 is the second process. So this is a constant volume or isochoric process. Expansion or heating process, it doesn't matter. So this is step 1. For step 2, we write what are the required equations, or maybe what are we supposed to find from the question. So step 2. The first one is the quality at the initial state. So initial means state 1. So the first item is to find the quality X at the initial state, means state 1. So X1, or quality at state 1, is a property, property at state 1. So when we do step 3 later, for state 1, we make sure that we can calculate for the quality at state 1. Number 2, the total amount of boundary work. So the work net total is simply the addition of both thermodynamic processes. So the first one, from state 1 to state 2, is the isobaric process, and then we add it with the second process, which was the isochoric process. So work state 2 to state 3. So for each process, write down its boundary work equation. So for the first boundary work, for the isobaric process, we know that boundary work for isobaric process is the pressure multiplied with the change in volume. Okay, or we can write it also in the specific volume form. Okay, so this is also equals to the mass. Okay, since the mass is constant, we can factorize it, multiply with the pressure, constant pressure, and now the change in specific volume. Okay, so we can either use each one. Okay, either use the volume or specific volume, but since property is when we find the properties later, we will find the values for specific volume. So I prefer to use the in terms of specific volume. Okay, and then for the isochoric process we know that the boundary work is automatically 0, so we can write it 0, and here actually we can cancel the term. Okay, so this is step 2. Okay, when we try to write the equation, so the important is so that we can see which properties which we have to find later. Okay, we have to find the pressure, we have to calculate for the volume, or maybe we have to find for the specific volume. The mass is already given from the questions. Okay, now for step 3 is when we try to solve for the properties. Okay, so based on the equation, now is the time to determine the required properties. So start with state 1. Okay, what is known? The temperature, 8 degrees Celsius, and of course the mass. But the mass, remember, for closed system it's the same. State 1, state 2, state 3, the mass is the same. Okay, but we can still write it down. Alright, so remember, for phase change substances, okay, so currently our substance is the refrigerant. We have to determine the phase. Okay, so to determine the phase, we have to have two properties. So right now we only have one, the temperature. So we can open the table A11, okay, but we cannot check for the phase. So we don't have enough amount of information which will allow us to check for the phase. Okay, so at state 1 we cannot do anything. Okay, we cannot do anything, but we can still proceed with state 2. Because why? Because state 1 and state 2 is connected by a process. So if we cannot do anything at one state, and if there is a process involved, we can proceed to the next state. Okay, so at state 2 we don't know the temperature. Okay, for the pressure, since it's a constant pressure process, we do know that the pressure is supposed to be equal to pressure 1, but we don't know the pressure at P1, so we don't know anything here. But we do know that the volume is twice the volume at state 1, or in terms of specific volume, the specific volume is twice the specific volume at state 1. We do know this. Okay, but in terms of checking the phase, finding the properties, we do not have any enough information. Okay, but still do not panic. Okay, because why? We have a second process. So from state 2 to state 3, okay, we can still proceed. Okay, so state 3. Okay, so state 3, we do know the pressure, 1.2 mega, and also in kilopascal, 1200 kilopascal, and also the temperature we do know now is 60 degrees Celsius. Okay, so now we do have two properties. Okay, we have the pressure, we have the temperature. So now we can do what is required, which is to check the phase first. Okay, check for the phase. Okay, so we prioritize the pressure. Okay, so we prioritize pressure, so we table A12, okay, for R134A at 1200 kilopascals. We compare the temperature at state 3 with the saturation temperature. And if you were to open the table right now, we will find that it is greater, so the phase of the substance is superheated. Okay, so when the phase is superheated, we cannot use the same table. We have to change the table A13 for superheated substance. And now the pressure is in megapascal, and we know the temperature is 60 degrees. So look for table 1.2 megapascal. Okay, and if there is the temperature reading for 60 degrees Celsius, we will read for specific volume. Okay, now why do we read for specific volume? Because remember, state 2 and state 3 are connected by the isochoric process. So the specific volume or the volume for state 2 and state 3 must be the same. Okay, so that's why we read for the specific volume. So if I am not mistaken, it's 0.018404 meter cube per kilogram. Okay, so isochoric process, volume constant, and secara tak langsung, okay, indirectly, the specific volume will also be constant. So the specific volume here, okay, is equal to the specific volume at state 3. Okay, so now we have one property. Okay, one property which will help us to check the phase, but still not enough, we need two. Okay, so don't panic, we can still reverse. Okay, now we try to look at state 1. Okay, what can we do with this property now, which we can relate to state 1? So from the equation, the volume is twice, okay, the volume at state 2 is twice the volume at state 1. We can now calculate for the specific volume at state 1. Okay, because we know that the specific volume at state 2 is twice the specific volume at state 1. So the specific volume at state 1 is half, okay, the specific volume at state 2. So here is 0.0180188404 divided by 2, so we can get the specific volume at state 1. Okay, so now we have two properties. We have the temperature to allow us to open the correct table, and we have the specific volume which allow us to check for the phase. Okay, so opening the table A11, because we are using the temperature right now. So at 8 degrees Celsius, okay, since the question asks us to find the quality, so it should be a mixture. So meaning that the specific volume at state 1 here, when we compare to Vg, it should be less than Vg and it should be greater than Vf. Okay, it should be a mixture. Okay, because the question asks us to find the quality. Okay, so when we compare, okay, V specific volume at 1 with Vg less, with Vf greater, so it's in between, so it's a mixture. So when it is a mixture, we can use the equation of mixture. Okay, so we have to read for Vf and Vfg. Remember, Vfg is the subtraction Vg minus Vf, so we have to calculate it also. So using the equation of mixture, we can rearrange it. Okay, then we can substitute the values. So the values, I believe that you guys can read it. So the answer here we will get 0.159. Do not try to round the number. Okay, leave it at least 3 decimal points. Okay, we have to be very sensitive to the amount of quality. Okay, so this is the answer for the first item. All right, and the second value which we should read at state 1, okay, remember it's state 1 and state 2 is a isobaric process, and we require the value for pressure. So at state 1 we should read the pressure also. So since the phase is a mixture, the pressure should be equal to the saturation pressure. So here the value for saturation pressure is 387.88 kilopascal. Okay, so this value for pressure is now equal to the pressure at state 2. Okay, so here is 387.88. So now we have two properties. Okay, we have the pressure. We can open table A12 and then we can check for the phase. Okay, so that we can check for the phase. Because why we have to still check for the phase? Because the question asks us to sketch the PV diagram. Okay, so at state 2 right now. Okay, at state 2 right now. Okay, so we are going to open table A12. Okay, now at table A12 there is no 387.88 kilopascal. Okay, alright, there is no 387.88 kilopascal. What there is in table A12 is 360 and 400. So 387 is in between. Okay, so the value for our pressure right now is in between 387, sorry, in between 360 and 400. Okay, so what we have to do now is we have to interpolate. Okay, so we have to interpolate, okay, for Vg first, okay, and then Vf. Okay, but prioritize Vg first, okay, because we want to see the phase. We have to check with the highest value first. So for Vg, okay, for Vg we can read for the values at 360 and also 400 kilopascal. Okay, we can read for the values. So we have here 0.05738. Okay, 0.05738, and this is we want to interpolate, and there is 0.0 51201. Okay, 51201. Okay, and for Vf, okay, which for 387 we want to interpolate. Okay, this is 0.0007.841. Okay, 841, and this is 0.007907. Okay, 0.007907. Okay, so we have to interpolate for Vg and then for Vf, so we can compare with the specific volume at state 2. So now actually to save time, actually we can just look at the range here. Okay, so if we were to interpolate for both between both of these, we should get the values between 0.0. For Vg we should get between 0.0, maybe 55 or maybe 54. Okay, for Vg. Okay, and for Vf we should also get in between 78 and 79, maybe 785, maybe 787. Okay, we should get in between this. Okay, and to save time we can just do an estimation. Okay, do an estimation. So if we were to estimate Vg, this, the value for Vg is this. and we compare it to this, definitely this is less. Okay, so V2 here is less than Vg. And from our estimation, this value here, if we compare to Vf, is definitely greater than Vf. So state 2 is also still a mixture. Okay, we don't, to save time, we can do a bit of estimation. Okay, see the estimation. So when we compare, if we do interpolate and we get the values, we can see that it's still a mixture. Okay, so state 1 mixture, state 2 mixture, state 3 superheated. Okay, so next is to draw the PV diagram. Okay, so we have the PV axis. Okay, don't forget the saturation line. Okay, and then the line running through the PV diagram is the temperature line. So this is the low temperature. Okay, and then there is another temperature. Okay, let's say it's here, which is for state 3 right now. Okay, the 60. Okay, so for state 1, it's the mixture. Okay, so here is, alright, and this is the P saturation. Okay, which is equal to P1 and also P2. So the first process, heating process, okay, still a mixture. Okay, so here is state 2. And then, okay, so volume at state 2, specific volume at state 2. And then the isochoric, constant straight line to the superheated region. Okay, so this is the PV diagram for this question. Okay, so the final one is to substitute the value to calculate for work net total. So we know now that work net total is only the boundary work for the first process. So I use in specific volume form. So mass multiplied with pressure, specific volume 2 minus specific volume 1. So this is 4.5 kg. This is 387.88 kilopascal. This is 0.018404. This is 0.009202. And here we can get the answer 16.06 kilojoules. Okay, so there you have it, an example for the tutorial question subtopic 2.4. So thank you.